Today let us look at the design of simple parts, how to employ the basic equations that we have learned in the previous sessions. So we will look into some of the examples, that is directly we shall take up the problems. Directly we shall take up the problems. So all we are going to do here is determination of the geometry of the part, that is the dimensions, be it lateral dimension or longitudinal dimension based on the stresses induced. And we are going to look into only these three class of stresses: tensile, shear or compressive stresses. And your component also will be subjected to simple loading situation. By neglecting principal stresses, stress concentration or any fatigue loading. Okay, so we will address this separately in detail in the upcoming chapters. And of course, also we employ factor of safety. We may not exceed beyond 5. Just for the sake of solving problem, please remember this formula. We will discuss this maximum shear stress theory again later. Okay, so the maximum shear stress theory, it states that the yield strength in shear is 50% of the yield strength in tension, that is S suffix y. Shear in yield is equal to 0.5 times of shear yield in tension. Just remember this formula. So you can employ this in your design. Tau is equal to SSY by factor of safety. Okay. So these formulas will be used in determining the dimensions of the component. To begin with the first problem. See, here we have a rivet. Two plates are joined by a rivet, and they are subjected to tensile load of 50 kilonewton. And the material of the rivet and plate, they are same, plain carbon steel 10C4, whose yield strength is 250 MPa. You can go to data book, and for 10C4 you can find out this yield strength also. Okay, so the yield strength in shear is 50% of the tensile strength. This fact is very important. What do they mean by this? The maximum shear to which the component can be subjected here is 50% of the yield strength in tension, that is 250 MPa, and the factor of safety is 2.5 for both the cases. So by ignoring the stress concentration, we must determine the diameter of the rivets and as well as the thickness of the plates. Before proceeding, we must analyze this problem. So there are two parts for which we need to determine the dimension. One is the rivet and other is the plate. So what type of loading and hence the stresses to these two components are subjected to? You have to determine that first. Look at the problem diagram. The plates are, of course, they are subjected to tensile loading. So you can make use of stress formula, tensile stress formula. Sigma is equal to P by A. To determine the thickness. What about the rivet? The rivet is subjected to shear loading. Okay. So you have to make use of the shear formula, shear stress formula, to determine the tau is equal to P by A. So, but there are certain conditions imposed here. Both the plates and the rivets are made up of same material. When I subject the plate to 50 kilonewton, the shear stress in the rivet must not exceed 50% of tensile yield strength. That is, the maximum shear is 250 by 2. Okay, that is 125. On top of that, we also have to impose factor of safety. Right? We will see how to do that. So, in total, first determine the type of loading and hence the type of stresses to which the components are subjected to by analyzing the given situation. So this is the top view of the assembly. There are 3 rivets actually. Okay, there are 3 rivets and 2 plates you can see. So the given thing is loading, yield strength and factor of safety. So what is the permissible shear stress for the rivets? See, this is what the formula that we have learned, right? Tau is equal to shear stress by factor of safety has to be applied. What is the shear yield strength? That is 0.5 times of shear tensile yield strength. That is what? 125 by 2.5. So the maximum shear to which the rivets must be subjected to is 50 Newton per millimeter square or 50 MPa. So this is the permissible stress, and from this you have to calculate the diameter of the rivet. And please note that there are 3 rivets, so the load will be equally distributed. So P by 3, isn't it? P by 3 by cross-sectional area of the rivet. So they have just rearranged here. 3 into cross-sectional area pi by 4 d square into permissible stress tau equal to the load. Substitute the respective quantities and solve for d. You will get d. And why they have written 22, 20.6 or 22? See, there are standard dimensions of the rivets that are available or manufactured. Okay, so that is also available in your data book. Go to the chapter on rivets in the data book. So the one dimension which is close to 20 here is 22 mm. So we will choose 22 mm. Is it clear? Now we have to determine the thickness of the plate. So what is the permissible tensile stress? Yield stress by factor of safety, that is 100 Newton per millimeter square. So what is the effective cross-sectional area here? So you just see here, effective cross-sectional area is not the thickness into 200, because we have rivets here, right? So 3 times the diameter has to be subtracted from 200, and then you have to multiply T to get the effective cross-sectional area. Then you can solve for T and round off to nearest value, because manufacturing to 3.73 exactly is not economical. Okay, so that is why we'll round off. Fine. So this is the solution. Let's move on to the next problem. So here we have a link subjected to 25 kilonewton tensile load and made up of grey cast iron FG300. So it means 300 MPa ultimate tensile strength. Factor of safety is 3. We have to determine the cross sections of the link. That is, see, the cross section is shown here. You know this drawing convention, right? See, rather than showing on the right side or on the left side, okay. In this case, so we have an axial force, a P, right? So from the drawing convention, as you know, right, we can show the cross section in the main diagram itself. Okay. So what are the type of stresses that this P will induce in this link? So we have to analyze that. See, since P is offset from the axis of the central portion of the link, right? So we have an eccentric loading. Obviously, we can replace the eccentric loading by an axial force and a couple moment. That is, you will have a direct tensile stress plus bending stress. So superpose them and use that superposition equation by employing the factor of safety to evaluate the sections of the link. Right? So now FG300. So here we have to design against ultimate tensile strength with a factor of safety of 3. So divided by 3, the load P should not use a stress of over 100 MPa because the factor of safety is 3. Okay. So now what is sigma T here? Sum of tensile stress plus bending stress. That is P by A plus MBY by I. Right? P by A, P is load, cross-sectional area is the link, cross-sectional area T into 2 into T plus bending moment. What is the bending moment? See, of this with respect to central axis of the link, P into, that is load, 10 plus T, right? 10 plus T, central axis of the link. So 2T by 2 is T, so 10 plus T. Arm, moment arm. Y is actually distance of the outermost fiber from the neutral axis. That is simply T. okay, because that is where we will get maximum stress, divided by I. Since it is a rectangular cross section, moment of inertia formula is BdQ by 12. So here B is thickness T, depth is 2T whole cube by 12. Sigma T is 100 MPa, we have evaluated. Now you solve for T, you will get a cubic equation. You can solve that in your calculator. So thickness is nearly equal to 25.5 mm or 26 mm. Third example, we have an hydraulic press here. So there are two frames, identical steel plates are being used as frames. You can see in the side view, front view. Okay. So the maximum force P acting on the frame is 20 kilonewton. That is also shown here. The plates are made of 45 C8 with a tensile yield strength of 380 MPa. Factor of safety is 2.5 mm. Fine. See, when you apply P as shown in the figure, what are the types of stress? It is similar to the previous problem, link problem. You will have a tensile stress superposed with bending stress, right? So evaluate the permissible stress first. Factor of safety is given 152 MPa. Sigma T is equals to P by A plus MBY by I. So same as the previous one. Moment arm, you must be careful while you evaluate the moment arm. You have to evaluate it from the figure here. Okay. So 200 plus 75 is the moment arm into 75, because 150 is the thickness. Okay. So T by this 150 by 2 is the distance of the outermost fiber from the neutral axis. So you can solve it to get the thickness 5.26 or just 6 mm is the thickness. Okay. So if you have any doubts in this problem, you can ask me during the live class. These are the references I've used to borrow these problems. Thank you.